The next 1 hour would be just going over some of the programming model heuristics, and if time permits, and if Perlmutter permits, more importantly, we will do some hands-on. And I'll point out to you to some resources where you could just run it. These are very simple. And yeah, if you have time post all these lectures, and if you still have energy, you can take a peek at them. How many of you are succeeded in getting a compiler built? One? Like, did you go through the entire process of build and tested it?
I mean, it says done.
Okay, so you have the installation done. Okay. Any other lucky winners? 2, 3, 4. Okay, I'll take it that as a success. Other than me, anyone. So the Perlmutter's file system is a bit bad today, so that is expected from a pre-production machine. So yeah, when you get a chance, just follow these steps. This will just install the compilers, and this is the binary directory where you can just see the Clang++ compiler. That's the C++. So I'll come back to it later. So this is the slide, and this is the command that you need to pay attention to for the Perlmutter. How do you compile a SYCL or any C++ application? So there were a few questions that came up. So we have an MPI application. How do we get this passed with SYCL? So the answer is, all you need to pass is these fSYCL flags to your CXX flags. That's pretty much. So append all these fSYCL flags to your CXX flags, and an appropriate compiler. And that should get you running SYCL plus MPI. So this is just a snapshot of how you can compile a standard C++ code. I need you to pay attention to this C++ standard that we mentioned. This is implicitly defined. The C++ compiler. This is the flag which says that your source code has SYCL, so compile it accordingly. And this second flag, which says NVIDIA and all, is just telling what backend am I compiling for. So I have earlier told you that the SYCL can run on Intel, AMD, NVIDIA, and whatnot. So with this flag, you can just target code on A100, which is a Perlmutter. And this is the architecture that most of you might be passing with standard CUDA, right? So for A100, it's 80. If you're doing V100 on Summit, it's 70, and so on. So yeah, these are the most important flags that one needs to just check for. And the rest of them is just straightforward. Whatever you do for standard C++ applies to SYCL. One added bonus or advantage here is if you have an AMD GPU access to it, like a gaming card or somewhere on your university machines, you could do the exact same steps. All you need to do is load ROCm instead of CUDA, change CUDA to HIP. That's pretty much, and that will give you a SYCL compiler that works on AMD machines. And this is the compilation line. So if you pay attention, instead of NVIDIA, we have AMD GCNs and the architecture flag. That's pretty much. So just an added advantage. So the compiler that you just cloned already works for MI50 and MI100, if you want to know what supports in AMD. So yeah, if you had built the compiler, you would just add it to your paths. So these two lines takes care of it. The first one is to just add to the path, and the second one is just the libraries. So if you do these two steps, you can run this small SYCL test code, and that'll say whether your compiler was working or not. And if you see that it looks like a standard C++ code. Here you have int and all the C++. So as I said, like GPU device is a vector. You loop over it. So yeah, and I'm just creating a queue. So if you run this code on Perlmutter, with 1 node, 4 GPUs, you would see this output. So this output is being printed within a loop because, as I said, GPU device is a vector of devices that you query for, and you just start printing it. So this slide just tells you, did I build my compiler right? Is my SYCL implementation working or not? Moving on, let's switch to the second part. Do you have any questions regarding the first part? Like anything very basic related to SYCL or anything very generic? Okay. So the real challenge here is, or the real use case is, if you have a CUDA code, I mean, is there enough motivation to port it to SYCL? And what is the advantage? Because that's the questions one should be asking. Is it worth my time to even port an existing CUDA to SYCL? And what are the advantages and time investments? So I'll just give you some of the practical experiences that some of us have seen from porting CUDA to SYCL, time investment, and as well as the returns. So as I said, like one should make as much correlations as with CUDA for better understanding and ease of writing code in SYCL. So you are better known with these terminologies in CUDA. You have thread, block, and grid. Thread is the basic unit. Block is the collection of threads. Grid is just a collection of blocks, loosely speaking. So you have the equivalents in SYCL as well. So you just call it work item, work group, and ND range. This is the exact same terminology if you have seen OpenCL before. So yes, there is a one-to-one mapping from CUDA to SYCL. So wherever you have a CUDA application which uses this, you can just use this because the exact kernel implementation looks the same. So I would talk a few minutes about ND range, which is based on 3 components. Grid is a collection of blocks, right? ND range is just a collection of work groups. That's pretty much. So you have this hierarchy, and I've just mentioned here what happens with a warp. So many of you who have written CUDA might have at some point touched warps, sync warp function or warp primitives, anything related to warp. So it's quite friendly to use these days than in the old days. So warp is nothing but a very small subset of collection of threads. Let's just call it that way. So warp lies in between threads and blocks. That's the hierarchy. Similarly, a subgroup lies in between the fundamental block of work items and work groups. So work group is nothing but a subgroup is nothing but a warp, and subgroup is a collection of work items, a small subset of collection of work items. You can see from this chart. So a subgroup is just a part of collection of work items. So yeah, if you have warp primitives in CUDA, you can easily find subgroup primitives as well. So this way, if you write something in SYCL, this will be portable to any vendor architecture and with the same performance. That's the more important thing. I mean, anyone can write the SYCL code. The most important question is, do I get the same performance as CUDA? The answer is, since all these heuristics piggyback on standard CUDA, you should see the same performance. That's, again, theoretically speaking. So again, subgroups are nothing but a very same concept as warps, and it's a small collection of a subset of work items that that work together. So if you have come across terms such as warp divergence, warp primitives, all these apply to the subgroups as well. So all you need to do is just Google for subgroup primitives, and you will find the exact one-to-one equivalence. There are so many resources online. People have put in efforts to create these analogs. So if you can find warp equivalents, you can just replace them with subgroup equivalents. One more thing about subgroups is, why bother using subgroups? It's again, the same question as why bother using warps? If you have an answer for that, this slide is particularly redundant. So this is just another view of hierarchy. You have a work item, a collection of work items forms a subgroup. Collection of subgroups becomes a work group, and the entire thing is an ND range. So you can think of this as a thread, warp, block, and grid. And again, this is very loosely speaking and trying to establish correlations. So you have warp intrinsics. These are called warp subgroup collectives. So just go, and there is a reference documentation that I have posted in the Slack channel. You could find almost a working code examples what one needs to find for in most cases. Coming to the actual memory model, this is the bread and butter of CUDA, right? So you have global memory, shared memories, and register or private memory. How do these map to SYCL? So just refreshing memory here. In CUDA, you have register memory, which is particularly local to a thread. It's private to a thread. Shared memory is just all the subset of threads use it. And global memory is just the device memory, right? So you have the same equivalence in SYCL and exact same scope. So this table shows you that. And this is the table that I had took from the SYCL specification standards. These are being updated regularly, and this is the only resource that one needs to look into for anything related to SYCL. So similarly, like CUDA documentation, this is the documentation for SYCL. So I will just briefly go over the details. If you are allocating device memory, it's just visible to the device. It's not visible to the host. Same like if you allocate a memory using CUDA malloc. The host, it is nothing but a pinned memory in CUDA. You have the same equivalent in SYCL. Shared memory, it's exactly the same. Shared memory is not the same as the block scope shared memory I'm referring to here. This shared memory is the unified memory, which is both accessible or both seen by host and device. So you have the same thing in SYCL as well here. So you can see that it's accessible by both host and device. And you have other optional parameters where it says whether other devices on the node can see it. Can I even pass it to another device? If you're talking about CUDA peer-to-peer copies, if you have come across those, I'm talking about the equivalence of CUDA peer-to-peer copy here. So yeah, this table, if you look at it, pretty much covers if I allocate some memory, what is my scope? Can I do it or not? So this particular slide takes care of the memory requirements. So if you have all the memory allocations, deallocations, you can find equivalence in SYCL. So yeah, this is one particular example. If you have a CUDA malloc, how does that look like in a SYCL? So you just have the same pointer. You provide the source. So it's templated. So I remember I said it's C++. So you can have templates of the type, or you don't even need to use these. So if you look at the specs, that will show C style also. So yeah, all you need is a pointer, size, and the type. That's the same it looks like. One important thing is, as I said, that's a mistake. You need a queue, because queue is the one that actually allocates, computes, does copy operations. So this is the queue, and we need the queue for anything to do on SYCL. So here I just said that create a GPU selector. And one should ask the question, can I specify a CPU selector here? Yes. And that would make the entire code run on CPU in a parallel way. And the parallel processing units are just the cores, as you see it in the compute units on GPU. So it's truly a portable design when you talk about the performance. Moving forward, what does real code looks like if you write, and I have a standard example here. I mean, I'm not showing a vector. I mean, I'm in fact showing a vector array, similarly like CUDA. I mean, if it's pretty simple. If you just glance over it, it looks like a standard C++. This is the only header you need to include for SYCL. For anything you do it in the SYCL, this is just the single header, and it can coexist with C++ headers. So that's the header namespace, or you could just specify the namespace. These are the arrays that are valid on a host. So if you see the general structure of this code, you have both the device code and host code that is coexisting in the same source file. That's what I was telling you about C++ single source code of SYCL. So you could place everything in one source file and just compile it as a single binary object. So in here you have three data structures, arrays, A, B, and C, classic on the C++. Just fill it with some, initialize it with some numbers. The trick here is this, if you remember in the first slide, I said there are two memory models. One is USM, Unified Shared Memory, and the other is a buffer memory model. So this is the old traditional way of using SYCL, and the Unified Shared Memory is the most friendly and easier to use, which I'll come back in the next slide. But this is the old and traditional way of doing it. So buffer is the data structure. So once you initialize A, B, and C, the standard way to run on a device is you take the host arrays, copy to the device, run something there, copy back the results. That's the standard protocol, right? You do the exact same thing in here. So A, B, C are valid on host. So you need to copy them to the device. So you need a data structures on the device first. So these buffers act as those device data structures. So all you need to say is you create buffers, and these buffers are looking at A, B, and C. Okay? And as I said, most importantly, queue needs to be created because that's where you submit all the tasks. So, okay, most important thing, to access these buffers, you need accessors. So this is a bit of a terminology here. So you have buffers which are pure data structures, and these are the accessors which provides access to these buffers, if it makes it easier to read. So these three lines says, I am accessing buffer A, B, and C, and the modes are read, read, write. So I'm just reading A, B, and just writing it to C. That's how it's read. And this is the actual kernel call. In CUDA, you have triple chevron that is launching the kernel, right? This is the parallel 4 that is launching the kernel in SYCL, and this runs on device. But you launch it from host, the same as CUDA. So this is just a handler that you create here. And if you see, how many of you have figured that this looks like a lambda expression, C++ lambdas? Okay? Because that's the standard way of doing it. It's C++ standards. So you launch all the kernels using lambda expressions. And there is also another way, which is not so friendly, a functor method, if you are very friendly with functors. But yeah, I'm here using lambdas. So all I'm saying is loop over 1024, because that's the size of an array. And this is the index. So this 3 lines, 2 lines, just runs the kernel. And I'll talk about wait later. And this is just, you're just printing out the output. So going back to the structure again, you have the host arrays, you have the buffers, and you just read and write them for access, launch the kernel, view the results. So, and just the explanation here. I'll talk about wait here in a bit. One important thing here is queue. There are 2 modes for the queue to create. One is in-order queue, where you have FIFO, first in, first out, similarly like CUDA streams. But the default mode in SYCL is out of order, which means whatever you put in the queue, it will just start running, and that might be problematic. So it would not be a problem here, and you don't need a wait theoretically, because buffers will take care of the dependencies. So this buffer and the accessor method ensures that A, B, and C are ready first, and then it puts into the buffer. If these are ready in the buffer, then only the access will be provided. It ensures that the complete calculations are run before you start printing them. So all the dependencies between the availability of data, the accurate data, is taken care of with this buffer model. So you don't need to specify, okay, is my calculation done or not? So you do synchronizations, right? So you do CUDA device synchronize or CUDA stream synchronize. You don't need all that in SYCL if you use the buffer model, because the dependencies are taken care of. This is the USM memory model. which is the most friendly one because these are pointer based. You don't have the buffers access additional burden. So if you see, you have the arrays, initialize them with something. You created the queue. If you remember CUDA malloc, just search and replace CUDA malloc with these. That's pretty much, again, loosely speaking. So you create device arrays, A, B, and C. These are, again, just valid on device, same like CUDA. You do a memcopy. So A is a host pointer. Device A is a device pointer, right? So you just do a copy, like CUDA memcopy, and then launch the kernel, the same. And one important thing here is you need to copy the data back from device C to C and print it. If you don't do this, you will see garbage because device C is just visible to only device. So whatever applies to CUDA here, so you do a CUDA malloc here, you do a CUDA memcopy, you just do a kernel launch and a CUDA memcopy. The same, the protocols follow in here as well. There is one big problem with this entire slide is that since we are not using buffer model, there is a ton of race condition happening here because queue is constructed out of order. So it will allocate memory, it will start the copy A, B, it won't wait. CUDA memcopy waits for the copy to finish, right? So you don't need to do a synchronize. So if you launch a CUDA memcopy, it ensures that the copy is done. But in this case, it will not do that. It just launches the copy and then moves on. So the host thread actually launches the copy A, launches the copy B, and then starts running the kernel. If the copy is not finished, this entire kernel is garbage, right? Garbage in, garbage out. So one needs to wait for these to finish. We did not wait in any of these cases because the buffer model ensures the dependencies are correct. In the USM pointer method, you need to wait at some point. So you need to synchronize here before you launch the kernel just to ensure that the memory copies are finished. So I'll tell you where are the synchronization points. So if you see the same code, you create the queue out of order. Again, I was just telling you that out of order queues means that the runtime will just launch whatever it sees. It does not say that copy A first or B first, wait for these two to finish, and then launch the kernel, and then wait for the C to finish before you start printing. So none of these dependencies are checked. So it's the duty of the programmer to actually impose waits. So you put a synchronization point. And again, this queue is the handle. So you need to have a queue wait. This is the command. And this wait ensures that host device copies are complete before you start the kernel. And similarly, you put the same command after the kernel just to make sure that the kernel is finished. And you launch the copy. And then you again impose a wait. So this way, if you put 3 waits, you can get the right answers if you start printing C. The other way is just put in order as the property. So if you start putting in order as a property, this mimics CUDA streams. CUDA streams are FIFO, right? So first in, first out. So whatever task that you submit to the queue executes first. So A gets done first, B, C. So it's all in a synchronized manner. So you don't need those many waits. Again, since this is again a synchronous statement, you need to wait before because you're printing on a host, right? So similarly, you put a CUDA device synchronize. It's very similar to that. So there's quite a bit of flexibility of how you can write a SYCL program, but everything actually ties one way or the other with CUDA programming model. So I'll briefly talk about some practical aspects. We have about half an hour. So in a real case scenario, these are all like good for demonstration purpose, good for tutorial purpose, good for ATPESC purpose. But in a real example, HPC examples, how many of you use thrust library or used thrust library in the CUDA code? Okay. So the question is, of course, what do I do with the thrust? And the answer is, there is an equivalent for thrust. The answer is in standard STL library. So the standard STL library provides parallel STL algorithms. So you don't need a separate library. Whatever you have in the standard C++ library, which is std sort. So whoever have used thrust sort can just replace with std sort. And this will work on both host and device. So you just need one line here. And again, the queue is required. So you take the queue that you created, pass it here, you create a handle, and that's how you run the sort. So all the thrust algorithms, so at least I would say, to my experience, majority of the thrust algorithms maps to parallel STL library because they just share the design. So whatever works for parallel STL, they all work on GPUs. One important note here is that this one DPL library, which is nothing but a wrapper around parallel STL library, is open source, one. It's heavily in development, so some of the features work, some don't. So this is the GitHub link. You can just look at, I mean, do I have the support or not? Just do a search. So,
so first, I want to say I just really love that you guys I mean, that's what I would want to be writing, but I'm just curious whether this is even compliant, because in the standard library, when you call stored sort, it's not supposed to be asynchronous, right? You're both matching the C++ library, but not really following the semantics.
So this is synchronous. So it is blocking call by default.
So what do you need wait?
Oh, this is just a snippet from overall application. So the other threads might be running other stuff. So this queue wait. Okay, if you're just looking at these 3 lines, you don't need queue wait.
Okay.
That's the answer. So one important thing here is, this is the additional argument which gives you the parallel running of these algorithms. So if you just check parallel STL library, you would see a device policy or parallel policy. And that's what ensures to run this algorithm parallelly on a host or a device. That's the handle. Second is, yeah, all this looks good. I have a huge code base with several CUDA files, several kernels. How do I translate to SYCL? So you don't need to do a hand translation. There is a tool available for that. So you could just download Intel DP++ compatibility tool. You don't need file-to-file translation. It translates the entire project. So you can check some of these links when you have time. If you have a makefile, CMake, or whatever, all you need to do is just do that. This toolkit takes care of porting all the files that it sees needs to be ported, given the dependencies that is established by the makefile. So using this tool, like any readily available CUDA code, was ported to DP++. I have personally ported about like 6 to 7 distinct scientific applications. Chola is an astrophysics code. Autodoc is one biomolecular simulations package, GROMAX. So it's very easy, even just curious to see how a CUDA line looks like in SYCL if you don't know what the equivalent is. Rather than, I mean, I did personally myself that rather than checking up online, I just took this code, took this tool, ran it on a .cu file, and it spit me C++ code with SYCL in it. And that's the way I came to know, oh, this is the equivalent of it in SYCL, rather than me Googling it. I was lazy, in fact. So yeah, you could use this tool. It migrates the entire project. Again, it's not like you can just take that ported result, run it on like the supercomputers. One needs to clean it up. But again, 80 to 90% of the code is very efficient and still valid. So you just need to remove a few comments, change lines few here and there. So yeah, it's nothing like very hard to even understand. as I said, like Autodoc is a project, quite a famous project, and it has got quite a good traction with the COVID vaccine discovery. So I was just curious, like there is a CUDA folder with all these CU files. My question is, what if I had to run this on an Intel platform using SYCL or any platform per se? All I did is just took that tool, like within 15 minutes, I was able to translate the entire project. I mean, the timeline does not say because it's about 2 hours difference. Believe me, it's about 15, 20 minutes I was able to completely port the entire project. So you would see output with all these files which carries the exact same name. The way you can differentiate is this dp.cpp is the translated names of these CU files. So you can just run this right away. But for efficient execution, you can just open these files, clean it up yourselves to be like, if you want to host it. So it's that simple. So that's one of the practical aspects. The question is, I have third-party MKL library, sorry, a cuBLAS, a cuFFT. What do I do? And because I'm not writing pure CUDA code. So there's an answer to that as well. So, okay, mistake. So you have an open source project called 1MKL. Again, so anything you see with 1DPL, 1MKL, these are all part of Intel's tool system, ecosystem developed under one API. So, and again, this is open source project. You can find it on GitHub. So the main motivation here is you have a single interface, 1MKL library, which pretty much similarly looks like MKL if you have used MKL. So the APIs are very much the same. You don't need to learn anything. So if you do a like cuBLAS DGEM, you just replace it with the one API DGEM. So and rest of the arguments are one-to-one matching because everyone complies with LAPACK scheme or BLAS schemes. So the answer is you can use 1MKL, which piggybacks on cuBLAS or cuSOL or cuRAN. So you have a unified interface with MKL libraries, and it just works right away because they are running on the CUDA libraries or AMD libraries or Intel libraries. So you have a unified interface where you can just use it on any device. So that's the story with the math libraries. And here are some useful resources where you can find out. So this is the link to the CUDA tool I was just talking about. The entire project where you can download the compilers and all the MPI, MKL, everything. And as I said, CodePlay does a good bit of training material, so you can just look at how one can translate from CUDA to SYCL. This is a GitHub link, which you guys can use. So this has few training exercise, simple source files, where you can just run it on Perlmutter and see how SYCL code works. So this was created by my colleague Thomas. Thanks to him. We use this material everywhere. So 9 SYCL of hell, cycle in other words. So we have quite a bit of simple examples that you can just take each file, source file, edit it, run it on any machine you have access to. So now you know how to build the compiler. You have the source code just to try and run it on, like for example, Perlmutter. And if you have an access to an NVIDIA laptop, many of your machines which carries an Intel Gen 9 will readily run the device code. If you have an AMD gaming card, you could build the same compiler there. So again, you can feel free to give it a try. I would like to show a practical example of a real project. So this was created by one of the colleagues at Oak Ridge. So the motivation here is you have a CUDA code, and how does that look in SYCL? Okay, so this is an advection kernel, I believe. So this is the CUDA implementation. Okay, let me do that here. So if you see, you have a make file, you have a .cu file, which is what we expect from CUDA, and you have a advection.cu file. So I believe this is the driver main function, and this is where the kernel lives. So I haven't seen great detail in it though. So I will put a GitHub link to it. Remember that this project has hundreds, thousands of code. So even the GitHub does not even wants to index it if you view it online. So it has equivalents of CUDA, OpenCL, SYCL, OpenMP. So these are the 4 variations for each and every single code. So I just took one out of it, and let's see how it looks like. So this is the main file. I don't know if you guys are able to see it. Is this better? Okay. So you have a int main. So on the left you have a CUDA. On the right you have SYCL. I'll come back to the SYCL later. So this is the main function. You have the standard pointers. So this is the particular place where you allocate device memory. Okay. The CUDA mem copies before you launch a kernel. I have no idea why we have a CUDA device synchronize here, but this is the kernel launch. Okay. I want you to pay attention to how the CUDA launch is being done. So you have a triple chevron, you specify some dimensions, and the function arguments. All these are the function arguments. And you do a device synchronize because it is async with host, right? You need to wait for this kernel to finish. And this is the time it takes for you to run. The last one is copy back the results, free the memory. So that's the standard protocol. So let's jump into the kernel. So this is the CUDA kernel that you are launching. The arguments here, please pay attention to the shared memory allocations here. So you are doing the shared memory, which is particularly visible to the blocks, right? And you need to question yourself, how do I allocate shared memory in SYCL? The rest of them are just like, yeah, you have thread ID, block ID, and that's the standard CUDA stuff. So all this is the kernel. It does something. Let's jump into the SYCL side. Again, it's the single source file. So you have everything in the same source code. Let's say, where is the main? So we have the main function. Okay, the standard old way buffers. These are not really friendly. I would highly recommend not to use them. The easiest way, the clean way, is to use the pointers, USM pointers. So again, this is a redundant wait. I guess it's just translated from CUDA device synchronize. And the question that one needs to ask is the kernel launch. So this is the kernel launch in CUDA. So you see that these are the dimensions. So thread block size and grid size, right? It's exactly the same. So you mention these two and launch the kernel. And to launch a kernel, this is how you launch it. So q.submit. Every work that you do goes through the queue. So q.submit and the buffer accessors that I've just talked about. So blah, blah, blah. And the rest of the code is all in there. So it's exactly one-to-one copy. So this is the kernel, right? Let's see from here. So you can see a great deal of one-to-one mapping of how thread ID, block ID, and rest of them map. So like the entire code is pretty much the same. All you need to find out is what are my equivalents of a very CUDA specific built-ins, which is block ID, thread ID, and how do they look in SYCL. So, and you have a barrier which equates to sync threads. Sorry. And you see the same, so you use sync threads because of shared memory, right? Before you do a load and store operations of sync with shared memory, people use, and it is mandatory to use sync threads to ensure synchronization. So sync threads is nothing but barrier, and it says local space, which is nothing but shared memory. So that goes on. And yeah, if you see, the rest of the code is pretty much exactly the same. And this is the barrier for sync threads in here. So yeah, I mean, if you follow the source code, it's pretty much the same. You don't need to design it in a new way. If you have an existing CUDA code, the entire code exactly looks the same in SYCL. So you just need to find what is the equivalent of thread ID, block ID, or whatever the CUDA says. So yeah, and I have about 15 minutes. It's post-lunch, so I would not bother. A lot of work already. So please give it a try with the compilers, and you have the GitHub link in here.
You have 45 minutes, huh?
Oh, okay. let's do the examples then. Can someone just, can everyone clone this GitHub library, and then if you're done with building the compiler, which is a great deal of effort now. So let's use the 45 minutes for building the compiler, and if possible, and we should probably test these examples. If you have your own source code, if you want to port it to SYCL, so I'll just go back to the instructions for the compiler, because majority of you are not done with it. It's painful.